In this video, we're going to give a rigorous definition of the integral of a real-valued function over a rectangle. A rectangle being a box in Rn. So suppose that we have a rectangle Q, which is A1, B1 cross A2, B2 cross all the way to AN, BN. This is a rectangle in Rn. Okay. Each of these intervals is called a component interval. And we define the width of the rectangle Q to be the maximum of the numbers B1 minus A1, B2 minus A2, up to Bn minus An. Then when we take the product, B1 minus A1 to Bn minus An, this product is denoted V of Q, and it's called the volume of Q. So if n is 1, then you just have a closed interval, and then the length is the volume of the rectangle. And then if you have R2, then you just have a rectangle in R2, and then the area is the volume. And so the volume is a more general notion than the length and area, right? The length and area are examples of volume. Okay. Now we define a partition. So suppose that we have a closed interval in R, then a partition of this closed interval is a finite collection P of points of this interval that includes the points A and B. Okay, and we usually call A T0, and then it goes up to TK, say, which is B. So each of these intervals, Ti minus 1 to Ti, that's called a subinterval determined by P. So that's a partition of a closed interval. Now more generally, suppose that we have a rectangle in Rn. So we have the rectangle Q as above. Then a partition of n, a partition of Q, a partition P of Q is an n-tuple P1 through Pn, where each P sub j is a partition of the interval Aj, Bj for each j. Now we can use the partition to define subrectangles if for each j, ij is one of the subintervals determined by p sub j, right? It's one of the subintervals determined by p sub j of the interval aj to pj, then the rectangle R, which is I1 cross IN, is called a subrectangle determined by P. This is a subrectangle of the rectangle Q. And the maximum width of these subrectangles is called the mesh of P. Of the partition. Okay, so just some terminology associated with partitions. And now we define a lower sum and upper sum. So let's say that you have a rectangle Q on Rn, and let's say that f is a bounded function from Q to the real numbers. And let's say that you have a partition P of Q. So you have all these subrectangles R of P. So for each subrectangle R determined by the partition P, let M sub R of F be the infimum of f of x, where x is in R, and capital M R of F be the supremum of f of x, where x is in R. So we define the lower sum and the upper sum of f determined by P to be L of Fp is the sum over all the rectangles of M sub R, little m sub R of F times V of R. And then U of Fp is the sum over R of capital M sub R of F times the volume of R. So what you're doing is, so let's say that you have a rectangle, say Q. So you have this rectangle Q, okay? And you take a partition like this, say. So this partitions Q into 12 pieces, and you have a function defined on Q. So what you do is you look at you take each rectangle, say this rectangle, you look at the biggest and smallest values of the function on this rectangle. So for instance, for the lower sum, you take the smallest value of the function. So that's this little m sub R of F. you take the smallest value of the function on this rectangle and then multiply it by the area of the rectangle. And you do that for all the rectangles, and that gives you this lower sum L sub fp, or L of fp. And then for the upper sum, you take the biggest value of the function on this rectangle and multiply by the volume of the rectangle, and then sum over all the rectangles, and that gives you this upper sum. Okay? So each partition gives you this lower and upper sum. Now once you have a partition, so let P, so let's say that your partition is P1 through Pn. So in this example that I drew, n is 2, so you have P1 and P2. Now suppose that we have P double prime. If P double prime is a partition of Q obtained from P by adjoining additional points to some or all of the partitions P1 through Pn, then P double prime is called a refinement of P. Now let's say that you have two partitions P and P prime. So let's say P prime is P1 prime through Pn prime. Given two partitions of Q, the partition P double prime, which is the union P1 union P1 prime to Pn union Pn prime, that's a refinement of P and P prime. Is this P prime is called the common refinement of P and P prime. So here's a little picture just to illustrate what's going on. So again, let's say this is our rectangle Q, and let's say that you have a refinement P like this. So let's say that's our, sorry, not a refinement, a partition. So this is Q. And let's say that you have Q again, and your partition P prime is like this. Okay, so this is P prime. Then when you take P, so here's the partition P, but then you add P prime like that. This is P double prime. That's a common refinement of P and P prime. That's the common refinement, right? It's a partition of Q. It's a smaller. It breaks Q up into more of these subrectangles. And so naturally, what will happen is that the lower sums will decrease, because now, so if you look at the lower sum of P and then the lower sum associated with P double prime, for the lower sum for P, you're taking the smallest, in these big rectangles. Oh wait, hold on, sorry. It wouldn't make the lower sum smaller, it would make the lower sum bigger, wouldn't it? Because for P, you're taking the smallest value in this entire rectangle, Whereas here, you're taking the smallest value in each rectangle. But here you were taking the smallest value in the entire rectangle. So for instance, let's say that the smallest value, let's say that in this rectangle, the smallest value was like 2. And then here, the smallest values were 2, 3, 4, and 2. Well, when you take the lower sum associated with this common refinement, since the smallest value in these rectangles was bigger than the smallest value in this entire subrectangle, the lower sum will be bigger, right? And similarly, the upper sum will decrease when you pass the common refinement, because for the upper sum, you're taking the biggest value in the box. But when you break up that box, okay, this subrectangle into 4 smaller subrectangles and then take the biggest value, those biggest values will be less than or equal to the biggest value in the entire in this entire subrectangle. And so what happens when you pass the common refinement is that the lower sum will increase and the upper sum will decrease. So let's just write that down. That's like a lemma. So let's say that P is a partition of Q. And F from Q to R is a bounded function. So if P double prime is a refinement of P, then the lower sum associated with P is going to be less than or equal to the lower sum associated with P double prime, and the upper sum associated with P double prime is less than or equal to the upper sum associated with P. Okay. So that's how the lower sums compare and the upper sums. Now, what happens when you're comparing upper sums and lower sums of 2 partitions? So we have the second lemma. If P and P prime are 2 partitions of Q, then the lower sum is less than or equal to the upper sum. So it doesn't matter which partition you pick 2 different partitions, the lower sum is always going to be less than or equal to the upper sum. The proof of this works like this. First of all, if P is equal to P prime, then we see that this is true, because if P is equal to P prime, then you're just taking the lower sum and the upper sum. Now, since this little m sub r of f is less than or equal to the capital M sub r of f, by definition, right, you're taking the infinite soup, then, okay, that's the reason why the lower sum is less than or equal to the upper sum. Because you have a constant number here that's less than or equal to the number here times the volume, and then you're summing over all the rectangles, right? So if P is equal to P prime, then the lower sum is less than or equal to the upper sum. But suppose that they're different. Then what you can do is you can take the common refinement. Of P and P prime. Then the lower sum associated with P is less than or equal to the lower sum associated with P double prime. That's what we said before. And since P double prime is a partition of Q that's less than or equal to the upper sum of F associated with P double prime, and that's going to be less than or equal to the upper sum associated with P prime by the lemma that we saw before. And so therefore we see that this lower sum is in fact less than or equal to the upper sum. Now we can finally define the integral, which is the main thing that we're getting to. So again, we have a rectangle and we're considering a bounded function f from q to the real numbers. And we define this lower integral like this of f to be the supremum of the lower sum of f associated with p, and we're defining this upper integral to be the infimum over all partitions of q, all partitions p of q, of the upper sums. Okay? So this is called the lower integral. This first one's called the lower integral of f over q. See, notice that this does not depend on the partition. This is a supremum over all partitions of the rectangle. And this integral with the bar above is called the upper integral of f over q. And these exist, right? These are not infinite, because the lower bound, the lower sum is bounded by any upper sum. So the supremum is bounded by any upper sum. And then similarly, the infimum of these upper sums is bounded below by any lower sum associated with any partition. Okay, so in general, we have that this lower integral is less than or equal to this upper integral. Now suppose that they're the same. If this lower integral equals the upper integral, we say that f is integrable over q, and we define the integral of f over q to be this common value. And in this case, we would write the integral like this. Now notice that I don't have a dx or anything like that. We'll talk about that later, but for us, we're just going to write the integral like this. The integral of f over q. So for instance, let's say that you have f from this closed interval. So this is your rectangle q, right? So f is a function from r to r, or well, really just from the closed interval a to b to r. And you look at the graph of the function, then what happens is that you have the lower sum. That's what you get when you take a partition and then you take the smallest value of the function. So the lower sum here would be this. It would be this value times the width of this rectangle, so it gives you the area of this piece. And then for here, you have something like this, right? Here you have something like this, and then here you have something like this, that would be the lower sum associated with this partition. And when you take the biggest values, so this would be the biggest value, this would be the biggest value, and this would be the biggest value in this piece, and this would be the biggest value in this piece. This area is the upper sum. And the definition of integrable mean f is integrable if when you take these sums over all the partitions, the supremum of the lower sums is equal to the infimum of the upper sums. And when that happens, then that integral is thought of as the area under the curve. And similarly, if you have a function from a rectangle in R2, right, you can have a similar interpretation. And let's just do an example. So suppose that we have this closed interval from 0 to 1, and we define f to be 0 if x is rational, and 1 if x is irrational. Well, what's going to happen is, so here's this interval from 0 to 1. When you take the partition, any partition of this interval, when you take the smallest value of f on each interval, each subrectangle here, right? Each of these subrectangles is going to contain, so each subrectangle contains both rational and irrational numbers. So because of that, the lower sum is always going to be equal to 0, because the minimum value, the infimum of the function on each subinterval is just going to be 0. And so when you take 0 and then multiply by the length of this interval, you just get 0. So every lower sum is 0. And what about every upper sum? Well, every subrectangle contains an irrational number, and so you're always going to attain the value 1. So every upper sum is just going to be 1, because you take the value 1 on each of these subrectangles, and then when you multiply by the length of each subrectangle, okay, you just get the length of the subrectangle, and then when you add up all those lengths, you get the length of the entire interval, which is 1. So since every lower sum is 0 and every upper sum is 1, we see that this function is not integrable. Over, well, at least over the closed interval I. Okay, that's a pretty long enough video as it is. In the next video, we're going to talk about conditions for which the integral exists. So the definition is not the best way to decide if a function is integrable. We're going to see other ways of working with this definition, equivalent definitions of integrability. Okay, thanks.